Our planet is enveloped by an invisible force field, a protective bubble we call the Earth's magnetic field. This field shields us from harmful solar radiation. Life on Earth exists because of this protective layer. Without it, our planet would be a barren wasteland. Imagine Earth as a small boat navigating a raging river. The solar wind is a stream of charged particles from the sun. Our magnetic field deflects this current. This shield allows our fragile craft to sail safely. The Earth's magnetic field is generated deep within our planet's core. This core, a sphere of molten iron and nickel, spins and churns, creating powerful electric currents. These currents generate the magnetic field, forming the magnetosphere. This magnetosphere is our first line of defense. It impacts everything from our atmosphere to our technology. The Sun, the star of our solar system, is not a silent, benevolent neighbor. It is a raging inferno, constantly spewing out a stream of charged particles, primarily electrons and protons, in a phenomenon known as the solar wind. These particles carry energy and magnetic fields of their own, and their interaction with Earth's magnetic field creates a dynamic and ever-changing environment. Imagine these charged particles as dancers, swirling and twirling in the vast cosmic ballroom. Earth's magnetic field acts as the dance floor, guiding their movements and influencing their steps. As the charged particles approach Earth, they encounter the magnetic field lines. Instead of a head-on collision, these particles are forced to spiral along the magnetic field lines, their movements dictated by the invisible forces at play. This interaction creates a spectacular light show in the polar regions known as the auroras, the northern lights, or aurora borealis, and southern lights, or aurora australis. The colors we see are the result of excited atoms in the atmosphere, energized by the collisions with these charged particles. The auroras are a beautiful reminder of the constant dance between Earth's magnetic field and the solar wind. The relationship between Earth and the Sun is one of a delicate balance. The Sun, while the source of life-giving light and warmth, also poses a constant threat with its powerful outbursts of energy. Earth's magnetic field, our invisible shield, plays a crucial role in maintaining this balance. It protects us from the worst of the Sun's fury, allowing life to thrive on our planet. However, this balance is not static. The Sun's activity varies in cycles, and during periods of heightened activity, it can unleash powerful solar storms that have the potential to disrupt our technological way of life. Understanding the dynamics of this relationship is crucial, especially in our increasingly technology-dependent world. Imagine a world without electricity, GPS navigation, or satellite communication. That is a potential consequence of a severe solar storm impacting Earth. The charged particles from these storms can disrupt our power grids, disable satellites, and even interfere with radio communications. The study of space weather, the ever-changing environment around our planet, is vital to understanding and mitigating these risks. By monitoring the Sun's activity and understanding how it interacts with Earth's magnetic field, we can better prepare for and potentially lessen the impact of these solar events. The Sun, our life-giving star, is not always a benevolent neighbor. Like a slumbering giant, the Sun can unleash sudden bursts of energy known as solar storms. These storms can have profound effects on Earth and its technological infrastructure. Imagine a sudden violent eruption on the Sun's surface, releasing a torrent of energy. That, in essence, is a solar storm. Imagine a sudden, blinding flash of light on the Sun's surface, releasing a surge of energy that ripples across the solar system at the speed of light. That is a solar flare, a sudden and intense burst of radiation emanating from the Sun's atmosphere. These flares are often associated with sunspots, cooler regions on the Sun's surface marked by intense magnetic activity. Think of them as short-lived but powerful explosions, releasing energy across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. While most of the harmful radiation from solar flares is absorbed by Earth's atmosphere, These events can still disrupt our technology, particularly radio communications. Imagine radio signals suddenly fading or becoming garbled, interrupting communication networks and navigation systems. That's the potential impact of a solar flare. These flares can ionize Earth's upper atmosphere, interfering with the propagation of radio waves and causing disruptions that can last for minutes to hours. The intensity of solar flares is categorized using a letter number system, with X-class flares being the most powerful. These X-class flares, though relatively rare, can cause significant disruptions to radio communication, especially on the sunlit side of Earth. While not directly harmful to life on Earth's surface, solar flares highlight the sun's unpredictable nature and the potential vulnerability of our technology to space weather events. Imagine 1 billion tons of superheated plasma, a swirling mass of charged particles, and magnetic fields erupting from the sun's corona and hurtling through space at millions of miles per hour. That is a coronal mass ejection, CME, a spectacular and potentially disruptive solar phenomenon. Unlike solar flares, which are bursts of radiation, CMEs involve the expulsion of vast amounts of solar material into space. These massive eruptions can travel at speeds of up to 2,000 kilometers per second, taking several days to reach Earth. When a CME reaches Earth, it can interact with our planet's magnetic field, causing what is known as a geomagnetic storm. Imagine Earth's magnetic field, our protective shield, being buffeted by a massive solar wind shockwave. That's the essence of a geomagnetic storm. The intensity of these storms depends on the strength and direction of the CME's magnetic field. During a geomagnetic storm, Earth's magnetic field can fluctuate dramatically, inducing electric currents in power grids, pipelines, and other long conductors. These induced currents can overload power systems, causing blackouts and disruptions to critical infrastructure. Imagine city lights flickering and dying as power grids are overwhelmed, or GPS satellites malfunctioning, sending inaccurate location data. That's the potential impact of a severe geomagnetic storm triggered by a CME. In the aftermath of a solar flare, or CME, the sun can unleash a barrage of high-energy particles known as solar energetic particles, SEPs. These particles, primarily protons and electrons, are accelerated to near-light speeds by the powerful magnetic fields associated with these solar events. Imagine a swarm of microscopic bullets, each carrying a tremendous amount of energy, hurtling through space at incredible velocities. That's the essence of SEPs. While Earth's atmosphere and magnetic field provide significant protection from SEPs at the surface, these particles pose a significant risk to astronauts in space, and even passengers and crew in high-altitude flights. Imagine a spacecraft, orbiting Earth or on a voyage to another planet, being bombarded by these high-energy particles. SEPs can penetrate spacecraft shielding, damaging sensitive electronics, disrupting onboard systems, and posing radiation hazards to astronauts. Even at aviation altitudes, where the atmosphere is thinner, SEPs can increase radiation exposure for passengers and crew, especially during transpolar flights that pass through regions of weaker magnetic field protection. The impact of SEPs highlights the importance of space weather forecasting and the need to develop effective shielding technologies to protect our astronauts and space-based assets from these invisible threats. In the annals of space weather history, the Carrington event of 1859 stands as a stark reminder of the sun's awesome power. Imagine a time before electricity was commonplace, when the telegraph, a revolutionary new technology, connected the world through a network of wires. On September 1, 1859, the sun unleashed a solar storm of unprecedented magnitude, forever etching its name in the records of space weather events. Richard Carrington, an amateur astronomer observing the sun from his private observatory in England, witnessed an extraordinary sight, an intense burst of white light erupting from a group of sunspots. This brilliant flash, now known as a solar flare, was followed by a coronal mass ejection of immense power, hurtling towards Earth at astonishing speed. Within 17 hours, the the CME slammed into Earth's magnetosphere, triggering a geomagnetic storm of unparalleled intensity. Telegraph systems worldwide went haywire. Sparks flew from telegraph wires, igniting fires and disrupting communications across continents. Auroral displays typically confined to polar regions lit up the skies as far south as the Caribbean and Hawaii, their vibrant colors painting the night sky with an ethereal glow. The Carrington event, though occurring in a technologically simpler era, serves as a stark reminder of the potential havoc even a single powerful solar storm can unleash. Fast forward to March 13, 1989. The world was a vastly different place, reliant on interconnected power grids and sophisticated satellite networks. Yet the sun reminded us once again of its unpredictable nature. A powerful solar storm, though less intense than the Carrington event, unleashed its fury on Earth, exposing the vulnerabilities of our modern technological infrastructure. In the early morning hours, a massive coronal mass ejection collided with Earth's magnetic field, triggering a geomagnetic storm that plunged the entire province of Quebec, Canada, into darkness. The storm's induced currents surged through power lines, overwhelming transformers and tripping circuit breakers. Within minutes, 6 million people were left without electricity, their lives disrupted by a power outage that lasted for 9 long hours. The Quebec blackout served as a wake-up call to the world, demonstrating that even a moderately strong solar storm could cripple power grids and disrupt our technology-dependent lives. It highlighted the interconnectedness of our infrastructure and the cascading consequences of power outages in a modern society. This event spurred renewed efforts to understand and mitigate the risks posed by space weather, leading to advancements in space weather forecasting and grid resilience. As if to underscore the point that solar storms are not merely historical events, the sun unleashed a series of powerful eruptions in October and November 2003, aptly dubbed the Halloween storms. These storms, though not as intense as the Carrington event, showcased the sun's ability to unleash multiple powerful eruptions in rapid succession, each capable of impacting Earth's technological systems. From October 19 to November 7, 2003, the sun erupted with numerous solar flares and coronal mass ejections, bombarding Earth with a barrage of charged particles and radiation. The intensity of these storms was such that auroral displays, normally confined to high latitudes, were visible as far south as Texas and Florida, painting the night sky with a kaleidoscope of colors. While the Halloween storms provided a spectacular light show for skywatchers, they also wreaked havoc on technological systems. Satellites experienced glitches and outages, airlines rerouted flights to avoid high radiation levels, and power grids experienced fluctuations, highlighting the vulnerability of our increasingly interconnected world to the sun's unpredictable outbursts. The Carrington event, the Quebec blackout, and the Halloween storms are not isolated incidents. They are echoes of the past, warnings for the future, reminding us that the sun, while essential for life on Earth, also possesses the power to disrupt our technological civilization. These historical solar storms serve as crucial data points, allowing scientists to study the sun's behavior, understand the potential impacts of space weather events, and develop strategies to mitigate future risks. By studying the characteristics of past solar storms, analyzing their effects on Earth's magnetic field and technological systems, and developing sophisticated computer models, scientists are continually working to improve space weather forecasting and provide timely warnings of potential disruptions. These efforts are crucial as we venture further into space, deploying astronauts and sensitive equipment that are vulnerable to the sun's unpredictable outbursts. The lessons learned from past solar storms are our guideposts, illuminating the path towards a future where we can better anticipate, prepare for, and withstand the sun's occasional tantrums. Deep beneath our feet, hidden beneath layers of rock and mantle, lies the engine that powers Earth's invisible shield, the Earth's core. Imagine a sphere of molten iron and nickel, twice the size of the Moon, churning and swirling in the heart of our planet. This fiery furnace generates the magnetic field that envelops our planet, acting as our first line of defense against space. This magnetic field is a constantly shifting force, generated by the motion of the molten iron in Earth's outer core. Think of a bicycle dynamo. As the wheel spins, it creates an electric current. Similarly, Earth's rotation and convection currents generate electric currents, creating our magnetic field. This process, known as the geodynamo, is complex and not fully understood. Earth's rotation, core heat, and molten iron movement are key to this planetary generator. This dynamo shields us from the sun's charged particles, allowing life to thrive. Without it, Earth would be a barren wasteland, stripped of its atmosphere by solar wind. Earth's magnetosphere, an invisible bubble of magnetism, shields us from the sun's charged particles, allowing life to flourish. Earth's magnetosphere is dynamic, forming a bow shock on the sun-facing side and a magnetotail on the opposite, storing solar wind energy. Intense solar activity can overload the magnetotail, causing geomagnetic storms that disrupt power grids and satellites. Earth's magnetic field guides solar wind particles towards the poles, creating auroras and protecting us from direct solar impacts. This magnetic ballet prevents a head-on collision with our planet, showcasing the field's protective role. Earth's magnetic field and atmosphere work together, deflecting solar wind and absorbing harmful radiation. This multi-layered shield is crucial for life, though regions near the poles remain vulnerable to space weather. A geomagnetic superstorm could collapse power grids, leading to prolonged blackouts, water shortages, and disrupted transportation. Hospitals and emergency services would struggle, highlighting the need for preparedness against such events. Satellites, vital for communication and navigation, are vulnerable to solar storms, risking widespread outages and disruptions. A Carrington-level event could damage satellite electronics, affecting TV broadcasts, internet, and GPS signals. Major solar storms could disrupt transportation, communication, and financial systems, leading to global chaos. The interconnected nature of our world makes us highly susceptible to the cascading effects of such events. Preparedness is key to mitigating solar storm risks, requiring improved forecasting, infrastructure hardening, and disaster planning. Investing in research and international collaboration can help us better withstand future solar events. Space-based observatories monitor the sun, providing early warnings of solar activity to help us prepare for potential impacts. These sentinels track solar flares and CMEs, crucial for space weather forecasting. Sunspots indicate solar activity, with intense magnetic fields leading to solar flares and CMEs. Predicting these eruptions helps us prepare for their potential effects on Earth. Forecasting space weather is complex, with vast distances and the sun's changing magnetic field posing significant challenges. Resilience requires hardening infrastructure, developing backup systems, and raising public awareness about space weather risks. Preparedness measures can help protect our technology-dependent society from solar storms. Earth's magnetic field has protected life for billions of years, but its dynamic nature introduces uncertainty. As we rely more on technology, understanding and preparing for space weather becomes increasingly crucial. Section 2. The ever-present threat. A call for vigilance and innovation. The sun, that life-giving star, can also disrupt our technological civilization. We live in an age of unprecedented technological interconnectedness, vulnerable to space weather. A Carrington-level event could plunge us into darkness for weeks or months. It's a call to action to ensure the resilience of our infrastructure. Advancements in forecasting and engineering are making us more resilient. Section 3. Our cosmic dance, respecting the sun's power, safeguarding our future. Our relationship with the sun is a delicate dance, balancing its life-giving energy and its awesome power. We often take the sun for granted, unaware of its constant influence. Understanding Earth's magnetic field in solar storms reveals our deep connection to the sun. This cosmic dance is a dynamic interplay between the sun's energy and Earth's shield. We are part of a larger cosmic ecosystem subject to its rhythms. As we explore space, understanding space weather becomes crucial. Our future hinges on adapting to the sun's nature. This challenge demands global cooperation and scientific ingenuity. By embracing space weather awareness and innovation, we can ensure our cosmic dance with the sun continues.